Hey there! Ever wondered why most rockets separate as they ascend into space and beyond? Rocket staging is an important concept which builds upon the principles of the ideal rocket equation to allow higher payload fraction in a rocket. Let's get spacey. What we learned from previously analyzing the rocket equation is that exhaust velocity is key. However, it's close to impossible to get above a certain payload fraction without using rocket staging. So rockets, which go all the way up into orbit from the ground, with current technology, all use stages. Take for example the Saturn V, which had 3 main stages. The first 2 to get it into Earth orbit, and the last one that actually pushed the astronauts to the moon. Another good example would be the Falcon 9 rocket with 2 stages, which assist in getting the payload into Earth orbit. A good way of explaining rocket staging and its benefits would be by using the rocket equation on a 2-stage rocket and a single-stage rocket. Let's start off with a standard single-stage rocket. Here's a breakdown of the different masses, which starts with the mass of the payload on top, mass of the overall structure, and the all-important mass of propellant. Now let's give each of these a value, with 5,000 kilograms for our payload, 10,000 for structure, and 100,000 kilograms for the propellant. Let's also assume that exhaust velocity is 4.5 kilometers per second, or 4,500 meters per second. Now we can use the ideal rocket equation to find the delta V, which equates to 8,983 meters per second. Similar calculations have been done in the previous video, so check that out if you haven't. Now let's look at a 2-stage rocket. Here's the breakdown of the masses, and you can see that things are quite different. The payload mass still remains the same, but the propellant and structure is divided into 2 parts for the 2 different stages. Let's give these values just like our single stage example. The payload remains at 5,000 kilograms. However, the propellant mass of 100,000 will be split into 2, 50,000 in stage 1 and 50,000 in stage 2. The same goes for the structure mass, which splits into 5,000 on each stage. So with the masses arranged and the total mass being equal to that of the single stage rocket, let's find the delta V of our 2-stage rocket. The exhaust velocity we'll be using here will also be the same as the previous example. First, let's calculate the delta V of the first stage. Its initial mass would be everything here, all the masses. The final mass would be the sum of all the masses except the mass of propellant on the first stage, which would have been used up. Plugging this into the rocket equation, we get a delta V of 2,567 meters per second for the first stage. Let's do the same for our second stage. Here, the initial mass would just be the payload and the mass of the propellant and structure of stage 2. This is because the first stage would have been dropped off. The final mass now would be the payload mass and the structure mass of stage 2. Using these values with the rocket equation, stage 2 gives an additional 8,063 meters per second of delta V. To find the total delta V of our 2-stage rocket, add up the delta V values to get 10,630 meters per second. Comparing this to the delta V of the single-stage rocket, we get an additional 1,647 meters per second of delta V. That's an 18% increase. This means that the rocket can go farther with the same amount of propellant, or that it can take more payload with lesser propellant to its destination when compared to a single-stage rocket. So that's how staging plays a key role in keeping the cost of spaceflight low through increased efficiency. To learn more about the rocket equation we used in this video, check out our previous video on the rocket equation. Leave a comment below if you have any questions or suggestions. Like and subscribe if you feel like it, and until next time, stay spacey.